Thermodynamics. There's 4 laws, but there's no 4th law. So how can that be? Tell me. There is a 3rd one. How can you have 4 laws of thermodynamics but no 4th law? Oh, very good. The 0th law of thermodynamics. It's kind of common sense. The 0th law of thermodynamics basically states that if A is in equilibrium with B, and this is thermodynamic equilibrium, which means they're at the same temperature, and A is also in equilibrium with C, then what else do we know is true?
B and C already.
Then B and C must be in equilibrium. Pretty common sense, but it is it's something to keep in mind because sometimes that's what you need to solve the problem, and it doesn't always trigger. You think you don't have enough stuff. B also has to be in equilibrium with C. Pretty standard, but so then the first thermodynamics is basically that energy is conserved. During thermodynamics. Thermodynamic processes. Zainab, are you here now? Morning. Anna?
Yeah.
Bless you. No, the energy of a substance, a gas, liquid, solid, whatever. So first of all, let's talk about heat and temperature. So, what is temperature?
The movement of particles.
Okay, good. So we can think of it as the movement of particles. Is temperature the total energy of the substance? Because you can have an ocean that's the same temperature as a bathtub, right? They have very different amounts of energy. So then but does temperature have to do with energy? Yes. So how would you say temperature? Temperature is the average energy per particle of the system. Okay. So it's like an average of this energy. Now to find the energy per particle of the system, there's a formula. and as Austin says, it's kinetic energy. And it's 3/2 or 1.5 times kb times the temperature. So the temperature is related to the average energy of the particle, but it's not exactly. You have to multiply it by a constant. Can you see that one? So it's bad color. Bless you. The Boltzmann constant is 1.38 times 10 to the negative 23. So that's kb. And this EK can be misleading. It's not the total energy of the substance. It's just the energy of one particle of the substance. Yes, that might be a molecule, it might be electrons, it might be other things. Okay. So maybe we'll say internal energy. I'll just say per particle. Now, I'm not totally positive why the 3/2. Why didn't they just make the constant times 3/2? But the 3/2 kb is a constant, so as the temperature goes up, the internal energy per particle goes up and down. Turn to the person beside you and discuss how you would change this into the total energy for the whole thing. Bless you. So what do you think? How would you do it? Yeah, just multiply by the number of particles. Okay, so U, we call this U, and we'll say N, bless you, is the number of particles in the system. Okay, now something about Kb, Boltzmann's constant, is related to the gas constant, which I think you guys know from chem, right? R, big R?
Yeah.
Yeah. 8.31. Good. So Kb is equal to R over Avogadro's number. So R is 8.31 and Avogadro's, of course, is 6.02 times 10 to the 23rd. Have a good day. Okay, so if we want to turn this into something with R, how would we go about doing that? We've got N is the number of particles, Na is Avogadro's, R is the gas constant. It's really, like this R, the gas constant, is really the Boltzmann constant per mole instead of per particle, right? Kb is per particle. Maybe we should write that down. Kb is the constant per particle.
Why does physics get like use
Because we're physicists. We don't work with little piles of things in grams. We work with universes and quantum fluctuations. We don't need to reduce everything to grams. But we do work with moles in this case. So this is per mole. Okay, here's a question for you chemists. What is a mole?
like a human defined amount of?
Okay, human defined. Why do we define it in that amount? Why is it 6.02 times 10 to the 23?
Is it for the the molar mass of like a specific type of carbon or activity?
You need a better answer for this. If you're gonna be chemists, you need to know this. You guys really don't know? Have I told you what a mole is? Like what Avogadro's is? Yeah, it's good. You remember, kind of. Okay, get your calculator. What is the mass of a proton? Or a neutron? It's one. Let me look it up because we need to get it. We need to get it right.
1.6738 times 10 to the negative 27.
Okay, so let's do. Let's do atomic mass unit. Yeah, because you have to get the average of neutron and proton plus an electron. So it's 1.66. So put in 1.66 times 10 to the power of negative 27. That's the kilograms of one nucleon. Okay. But I'm using the AMU. Do you know what an AMU is? Atomic mass unit? What is that? Good. Carbon? Which carbon? 12, right? So an AMU is 1/12 of a carbon 12. But it's ostensibly the mass of one unit of an atom. You can think of it as the mass of a proton or a neutron, which you have to add. So that's in kilograms. How would we turn it into grams? So times that by 1,000. What do you get? 1.66 times 10 to the negative 24. So that's like the mass of a neutron or proton in grams. Now inverse that. Hit the x to the minus 1 button. What do you get? Yeah. So that's why Avogadro's number is Avogadro's number. Because it's the inverse of the mass of a nucleon. the reason we use that is because chemists know that when you have a reaction, this particle mixes with this particle, but only this many particles and that many particles go together, right? And so if you have a mole of this and a mole of that, and you mix them together, you're gonna get a mole of this and that. So if you have like a mole of, well, you'd have like 2 moles of hydrogen and 1 mole of oxygen. You put them together, you get 1 mole of water, right? What the Avogadros does for you is it makes the molar mass the amount of grams you have in your container. That's why chemists use moles. So they just work in grams in the laboratory. That's the only reason. Okay, blah 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 moles. This is particles, N. Na is Avogadros, and R is the gas constant. That's really Boltzmann's per mole, right? So how would we convert this into something with R? Yeah? Oh, say that again? Yeah, but which N? Yeah, little n, right? And which is the, what's the little n mean? Good, so this is number of moles. NRT, does that sound familiar? PV, right? So this is also equal to, I'm running out of space here, I'm not doing this very nicely, but 3 halves PV. And U, take it in that U is not the energy per particle. What is U? Good. We'll call it energy of the system. So not per particle, that's U is the energy for your whole substance, your whole sample. Good. Take 2 minutes and talk amongst yourselves. I'm gonna get coffee. See if you can read and explain that. Anybody else want coffee? Not today? You're back from spring break, you don't need coffee?
Believe it or not, I just need a lot of coffee. Yeah, but I'm trying to.
I don't know why they just can't sit.
I'm really addicted. Like, I realized that I'm really addicted. That's bad. It's bad.
Oh my god.
Cool. Stop this. This is a long one.